All right, let's get started. Okay, so I'm going to recap the basic picture of what we were doing last lecture, because this is really the key starting point for all of self-force calculations. This is the underlying formalism. This is where all the equations that we use come from. It all comes from this matched asymptotic expansions. So when I was showing you the adiabatic approximation and stuff, that's just kind of a hack to avoid having to know the self-force, but you do need to know the self-force to get the kind of accuracy that we need for Lisa science. And you also need to know it even to do an adiabatic evolution in Kerr, because in Kerr you need to know the evolution of the Carter constant, and you cannot get that just from balance laws by balancing energy or angular momentum in gravitational wave fluxes with local changes at the particle. Okay, so this is what's going to lead up to how we actually calculate the self-force in practice and how we actually calculate the metric perturbation in practice. It all comes from this, where our starting point is we want to solve the Einstein equations in this small region where r is much, much bigger than the small mass, or epsilon, but still much, much smaller than the external length scale set by the big mass. So we're in this buffer region here. Okay, and what we had found last lecture was in this buffer region, the exact metric could be written in the form of what I call the outer expansion, and then we're trying to find the local forms of H1 and H2 in the buffer region. We adopted local coordinates, so concretely we can use Fermi-Walker coordinates that are centered on a world line that will represent the center of mass of the small object. And we're writing things for small r, where r is just the usual radial coordinate related to the Cartesian coordinates x, y, z, like this. Okay, so the background metric, g, in these coordinates looks approximately like just the Minkowski metric. And then you have corrections of the form r times the acceleration of the world line that this is centered on, plus r squared times Riemann curvature terms. So this acceleration is the acceleration of the world line as measured in the external background spacetime G, and the Riemann terms are the Riemann curvature of G. Okay, then we had that H1 looked like m over r plus order r to the 0 terms, which will have the form r to the 0 times a times m, plus some other stuff that we'll explain as we go. The key thing is that a leading order looks just like a Newtonian potential m over r. And H2 has the form m squared plus epsilon ijk. So I'm kind of melding all the components together here. That's why the indices don't make any sense. But you have mass squared and you have the spin of the small object appearing at order 1 over r squared. And then, well, order 1 over r corrections. Okay, and I went through the reasoning maybe a bit quickly for why this starts at order 1 over r and why this starts at 1 over r squared. So that came from the matching condition. But you can imagine why you can't have a 1 over r cubed term, for example. So let's say H2 contained a 1 over r cubed term. this has to match something that was in the inner expansion. Then we have epsilon squared h2 is epsilon squared over r cubed. So this is the term, the full term in the metric. Always has the epsilon squared next to it. But this is using the unscaled outer coordinates. But it has to match something in the inner expansion if we write it in terms of scaled coordinates. So remember, our bar is r over epsilon. So if we rewrite this r cubed in terms of r bar cubed, we pick up an epsilon cubed in the denominator. And then we have 1 over epsilon r bar cubed. So if this were to match something in the inner expansion would have to include negative powers of epsilon. So it would have to be divergent in the limit epsilon goes to 0. But our whole assumption is that that's not the case, that we have a nice, well-behaved expansion in terms of r bar that looks roughly just like a power series in epsilon, with no negative powers. So we cannot have this. So we have to start at 1 over r squared. We cannot get 1 over r cubed, 1 over r to the 4, anything like that. And similarly, for the first order, the highest power of 1 over r we can get is just 1 over r. We cannot have 1 over r squared. Okay, so now solving the Einstein equation, we're going to get some key information. We're going to find out how the mass evolves with time. We're going to find out how the spin evolves with time. And most importantly, well, maybe not most importantly, but importantly, we're going to find what is the acceleration of the center of mass of the small object. It's also going to give us just more explicit versions of H1 and H2. And those are going to be crucial ingredients in the actual practical methods we use to calculate H1 and H2 globally, not just near the small object, and explicit local, and also sorry, I lost my train of thought there. So we're going to get the explicit local forms of H1 and H2, not just the schematic forms we have over there. And yeah, that's going to be key for the methods we're going to use to solve the Einstein equations globally in the whole space-time. Okay, so we had ended yesterday with an expression for this E alpha beta of h bar n. So remember, E was box h bar plus 2r alpha mu, beta nu, h bar mu nu. So this is what's on the left-hand side of the Einstein equation. And we'd found that it was at leading order in distance, just a flat space Laplacian operator, and then a sum over higher order terms that are higher order in R. So this is proportional to, or of the order R to the P times h bar n. Okay, so as I said last time, this is going to lead to a sequence of Poisson equations. So if we substitute an expansion that h bar n is a sum over powers of R, starting at order minus n. So for n equals 1, it's 1 over r. For n equals 2, it's 1 over r squared. R to the p h bar n p alpha beta, where these are now functions of t theta phi. But you can always replace the dependence on theta phi with a dependence on the unit vector n. So remember in the tutorial, I said that the unit vector n is just selecting an angle on the sphere. So we can always replace dependence on theta phi with a dependence on the unit vector. Okay, so we substitute this into this operator. This gives us a sequence of Poisson equations. So for example, at n equals 1, the very first equation we're going to solve is flat space Laplacian acting on r to the minus 1, h bar 1 minus 1 alpha beta equals 0. So this is just Laplace's equation. Then you're going to have a flat space Laplacian acting on the next term in r, which is r to the 0. And we're going to get these e superscript p terms, move them to the right-hand side of the field equation. And so then we'll have minus e minus 1 alpha beta constructed from r to the minus 1. Let me write it the same way I wrote it there. Constructed from h bar 1 minus 1. So you solve for the leading order term in r, then that acts as a source for the next term, and it keeps going like that. You keep having lower order terms acting as sources for the next term you're looking at. So for the general pth order, you have flat space Laplacian acting on r to the p h bar 1 p alpha beta. On the right-hand side, we have a sum over lower order terms, p prime from minus 1 up to p minus 1, so all the lower order terms. And then we have e superscript p minus 2 minus p prime alpha beta constructed from h bar 1 p prime. So don't really worry about the superscripts or anything. The key point is that you just have a sum over lower order terms or lower powers of r. P prime runs from the first power, the very first one, minus 1, up to one order lower than the order you're trying to solve for. So you can just solve this order by order algorithmically. Now to simplify the calculation, we're going to expand these coefficients, h bar and p, in a set of harmonics. So we could use ordinary spherical harmonics. And this simplifies our life because the spherical harmonics are eigenfunctions of the flat space Laplacian. So we have the flat space Laplacian acting on a spherical harmonic is minus L plus 1 over r squared YLM. So this takes differential equations and makes them into algebraic equations. Now it's key to realize that these harmonics are not defined from spheres around the big black hole. They're not defined on big spheres like this. They're defined on little spheres around the small black hole. So the angles I'm talking about, theta and phi, are the angles in the local coordinate system centered on the small black hole. Okay, so we're not going to quite use these harmonics, but we're going to use something very similar. N hat L. And what that is a product of L unit vectors and these angular brackets denote the symmetric trace-free piece of this product. So I went through this in the tutorial yesterday, but for those who missed it, just as an example, n hat ij is ni nj minus a third delta ij. And so when you take a trace of this, you get 0, because this is a unit vector, so this gives you 1. And then the trace of delta ij is 3, so you get 3 over 3, and you get 0. And you can write down similar expressions for any number of indices. So these sets of products of unit vectors are basically equivalent to a YLM, but they're a bit nicer to work with in Cartesian coordinates. So they satisfy the same eigenvalue equation. The flat space Laplacian acting on n hat L is minus L plus 1 over R squared n hat L. So we're going to write h bar n p alpha beta as a sum over L greater than or equal to 0 of h bar n p alpha beta L. So L just means I1 up to I lowercase l. Now these are just functions of time, and they're multiplying n hat L. So this is completely equivalent to sum over L, sum over M, h bar n p alpha beta, add an extra index here, L m y L m. So it's the same L here as the L over here. And the sum over m is basically accounted for the fact that you have a bunch of indices here. You actually have 2L plus 1 independent pieces, just like you have 2L plus 1 values of lowercase m in a spherical harmonic expansion. Okay, so let's substitute this into the equation we had over here, this Poisson equation. Now this was one of the exercises was to show what comes out of this this expansion. So now we have the flat space Laplacian acting on r to the p n hat L, and then these coefficients h bar n p alpha beta L. They only depend on time, so the Laplacian doesn't act on them. And then in the exercises, he showed that this is r to the p minus 2 times p plus 1 minus L plus 1 times n hat L. So that's just a couple lines of calculation, and you should make sure that you can show that's the case if you haven't already yesterday. So now let's also expand this right-hand side in the same set of harmonics. And in the concrete calculation, that's the hard part of the calculation. That's the part that's quite lengthy. Okay, so we're also going to expand E superscript P, alpha beta, H bar. So that can be written as sum over L. L is always non-negative. And I'm just going to write this formally as superscript P, superscript L, alpha, beta, L, H bar. So whatever things are in here, it's going to be given by this with now n hat L outside. Okay, so this equation here, we call that equation star. Star becomes just an algebraic equation, r to the p minus 2, p plus 1 minus L plus 1, H bar 1 P alpha beta L. Actually, this gets a bit confusing if L is 0, because then you don't have an index here. So I'm going to add a superscript L label just to handle the case where that's 0. Where did I write that expansion? Over here. Okay. Put in a superscript L here. Okay. So the left-hand side just becomes this. The n hat L's factor out from the entire equation. So you just have an algebraic quantity. Now you have the sum over lower order modes. P minus 2 minus P prime, alpha beta L. I'm just going to define this thing on the right-hand side to be S1 P L alpha beta L r to the p minus 2. So the overall factor here is always r to the p minus 2. Once you handle the derivatives that come into here, just like it's r to the p minus 2 on the left-hand side. So now this term cancels that term, and you just have a solution for this coefficient h bar 1 pl. So our solution is h bar 1 p l alpha beta l is equal to 1 over p plus 1 minus L plus 1. So I'm just dividing both sides by this this factor that was on the left. And now on top, we've got S alpha beta L 1 P L, just a function of time. Okay, so I'm leaving myself room because obviously this does not apply if this factor is 0, if the denominator there is 0. So this is if p times p plus 1 is not equal to L times L plus 1. If it is equal, then you just have an arbitrary function of time. It's just a homogeneous solution to the Laplace equation. So this is if p times p plus 1 is equal to L times L plus 1. As a small note, this is only an arbitrary function of time if the source is 0 for this particular mode. If it's non-zero, then you actually have to introduce a logarithm of r into your solution. And that allows you to solve it even if this is non-zero in the case that p times p plus 1 is equal to L times L plus 1. At first order, meaning n equals 1, that actually never happens. There are no logarithms at any order in R. But at second order, that does happen. Okay, so here I'm writing down the structure of the solution just for n equals 1. It's the same story for n equals 2. But now this S doesn't just depend on lower values of p, it also depends on lower values of n, meaning in this case n equals 1. So it's exactly the same, but the source 2pl is constructed from h bar 1 p l prime prime in addition to h bar 2 p prime l prime alpha beta, where this p prime is less than p. So the source now depends on lower order modes, both in the sense of lower powers of R, but also in the sense of lower powers in epsilon. And that's actually true not just for n equals 2, but for all powers of n. Or, sorry, all powers of epsilon. You always have the same structure. It's just that, okay, so what's the conclusion here? What's the punchline? Every single coefficient in our expansion, h bar n p l alpha beta l is a function of t for all n p l. Every single one of these, for all values of n, p, and l, is algebraically determined with no freedom by the modes, these special modes here, where p times p plus 1 is equal to L times L plus 1. So by the modes h bar n p l alpha beta l with p times p plus 1 equals L times L plus 1. So you have a set of special modes, and then every other mode to all orders in R, all orders in epsilon, is uniquely determined algebraically from these special modes that satisfy this relationship. Okay, so what are these particular modes? P less than 0, so this means negative powers of r. These modes appear in the metric in the form h bar n minus L minus 1 L alpha beta L n hat L over R to the L plus 1. So you can check that if P is minus L minus 1, then this is satisfied. So this should remind you of the form we had for just the multipole expansion of a Newtonian field. Where we had the Newtonian gravitational field of some matter distribution was m over r plus mi ni over r squared plus mij n I n j over r cubed, and so forth. So these multipole moments are typically defined so that they're symmetric and trace-free, and then I can replace that product with n hat ij. Now you see I have the same structure here that I've got here. This is, the power of r here is r to the L plus 1. So in this case L is 0, in this case L is 1, in this case L is 2. And then I have some n hat L, which is equivalent to a spherical harmonic with L equal to that L. That's what we got here. L equals 0, L equals 1, L equals 2. So these coefficients play the same role as the multipole moments here. So these are the multipole moments of the small object. So meaning of that inner background metric, G alpha beta object, the way we had them yesterday, or corrections to the multiple moments of the background spacetime G object. So all of these can be associated in some way with multiple moments of the small object itself. Now, what about the case where P is greater than or equal to 0? Those are going to have also a nice interpretation. For P greater than or equal to 0, these special modes appear in the metric in the form r to the L times h bar n p n l l alpha beta l n hat l. So rather than 1 over r to the L plus 1, we have r to the L. So these modes are growing with r as you move away from the small object, whereas the other modes were decaying with r as you moved away from the small object. Any general modes, they are uniquely written in terms of these special modes because of the formula I wrote down. From this, every single mode is written in terms of the source. The source is entirely constructed from lower order modes. So if you follow the chain back, eventually you're going to reach these modes. This is the only place where there's any freedom in your solution. So you always have either an arbitrary function of time, which is always one of these special modes, or you have something written in terms of the source, which is in terms of lower order modes, but those are always going to be constructed again from a source written in terms of lower order modes, or as an arbitrary function of t, and eventually you're going to get every single mode written in terms of these special modes. And the special modes, if they're decaying with r, can be identified as with multiple moments of the small object. If they're growing with r, then you can identify them as essentially pieces of a Taylor series of an external metric. So let's consider this case, or this picture in the Newtonian case again. So let's say we've got a small matter distribution, and we're considering Newtonian gravity. Then the total field is a field, the total field in this region around the small object is what's called a self field. That's a field produced by the small object itself, plus the external field produced by the big black hole, or not black hole, big matter distribution in Newtonian gravity. So phi s is what I wrote over there. It's a multipole expansion. Phi external, you can write as a Taylor series around the center of the small object. So it's phi external just at xi equals 0 plus di phi external at 0 times xi plus a half di dj by external 0 xi xj, and so forth. So you just perform a Taylor series of the external field. So the external field is created by this big object. And the small object creates what we call the self field in the neighborhood of the small object. Now these, maybe it's not obvious, but these have the same form as these. So say we replace this with an ni, then we have an overall r outside. So this is L equals 1, r to the 1, so that's the same form we have here, r to the L, n hat to the L. Then here, we replace these with n, I, and j, and we get an r squared out here. But now this has to be a solution to the Laplace equation. So actually, if you take the trace here, you get 0, because it's a solution to the Laplace equation. So that means this is trace-free. You put the angular brackets around there, which means that only the trace-free part of this product contributes, which means we have n hat I j. So this is r to the 2 and 2 indices on the n hat. So that's just like r squared and n hat ij. So we still have this form. So each term here can be interpreted as an external field, or a term that's in the expansion of an external field. So there's some subtlety here, what you mean by external, because we're looking at the metric perturbation created by the small object. So every term we're finding here is somehow sourced or created by the object moving around in the space-time. But locally, a certain piece of it, the piece involving these special modes, is indistinguishable from just some external gravitational field you've applied. So let's write things how I wrote them there, in terms of a self field and an external field. So let's write metric perturbation, Hn alpha beta, as Hs n alpha beta plus Hr n alpha beta. So here I'm using capital R rather than external, partly just because that's the tradition in self-force, but partly because you can see the self field can also appear like a singular field, because all of these solutions, if you take them to r equals 0, they're singular there. Whereas all these fields over here, with r to the L, if you take them down to 0, they're perfectly smooth at r equals 0. So you can think of, rather than a self field, you can think singular field. Rather than an external field, you can think of a regular field. That's why it's capital R. It's regular at r equals 0. So but it's important to keep in mind, all of this is outside the small object. We're not looking inside the small object, we're looking outside. But nevertheless, pieces of the field that we're seeing there look like a Taylor series of some smooth external gravitational field expanded around the world line that's at the center of mass of the small object. Okay, so more precisely, how am I going to define Hs and Hr? So first, let me define Hr. So this is the piece of Hn alpha beta that only depends, or only involves, let me say involves, only involves those modes over there. So it only involves those modes or nonlinear or linear combinations of them, because they feed into the source. So it only involves those modes or linear or nonlinear combinations of them. But the point is, in this solution that I'm constructing just by this algorithm, this is the piece that's not going to involve any dependence on those modes over there that are identified with the multipole moments of the small object. Then Hs contains all the dependence on the special modes over there, h bar n minus L minus 1, L alpha beta L. So it will also contain nonlinear contributions coming from multiplication of this with this. So this includes products of lower order h bar r modes with lower order h bar s modes. So this is a consequence of the nonlinearity of the Einstein equations. Okay, what are the properties of the S field and the R field? Well, H bar R is smooth, as I said, at R equals 0. And it satisfies the vacuum Einstein equation. Not just outside of the small object, but also at R equals 0. So this strengthens the interpretation of this as kind of an external field. It just looks like some external vacuum field in the neighborhood of the small object. So then, locally, we can define an effective metric, which is the external background, plus HR alpha beta, where HR alpha beta is just the sum of all the HRs, HRn alpha beta. So we can define this effective metric, G effective, which is a vacuum solution, a smooth vacuum solution so this thing here is what looks like just an external spacetime. If you were just sitting really near the small object, you would think of this as, this is just the external gravity acting on me. But as I said, all of H, including HR, is created in some way by the small object. So this is only an effective external metric. It's not just created by the big black hole. Then HS is like a local self-field. So this includes all the dependence, all the local dependence on the mass, the spin, the quadrupole moments of the small object. It doesn't satisfy any particularly nice field equations, unlike HR. So if we look at points not at R equals 0, well, the first order self-field, HS1, is a vacuum solution at all points off R equals 0. But at second order, you have just the difference between the second order Einstein tensor constructed from H1 and the second order Einstein tensor constructed from HR1. So this is not equal to the second order Einstein tensor constructed from HS1. So if you had this equal to this, then it would be a solution to the Einstein equations. But in this case, it is not. The difference between these two things is not equal to that. So the reason you have to subtract this term is that HR2 satisfies the equation that has this term. Okay, so in the literature, especially at first order, you'll see a lot of different definitions of the singular field and the regular field. The one usually used at first order is called the Detweiler-Whiting singular and regular fields. Those are defined from Green's functions, not at all from this method. But at first order, at every order in R that's being calculated, the two definitions are actually identical. They give you the same local terms in HS and in HR. At second order, there are also different definitions in the literature, and these definitions are actually not equivalent to each other. For example, there's a definition by Abe Hart that's actually not just in perturbation theory, but it's for the fully nonlinear Einstein equations. He defines a self-field and an effective metric, but that differs from what I've defined here because he actually does have that his self-field satisfies the Einstein equation, and he does not have that the effective metric satisfies the vacuum Einstein equation. Now that actually causes big problems if you go through the details of his paper, although it's not made clear in the paper. There's also a definition by Sam Gralla at second order, and again, his effective metric does not satisfy the Einstein equations. And it differs from the effective metric I'm talking about here in a more significant way that I'll get to in a second. But the key thing is, the way I've defined this, I'm just constructing a local solution algorithmically, and then I just define a convenient way of splitting it up into two pieces. You don't have to do that. There's no regularization of anything going on here. It's just I have a metric that involves two types of terms, and I just divide it up in a way that seems natural. But it's also a way that then has nice properties of the effective metric. So one nice property is that it satisfies the vacuum Einstein equation. Then another nice property I'll get to in a second, which is that the equation of motion for the center of mass is written just in terms of HR, not in terms of HS. So that's a consequence of my particular choice of HS and HR. If you made a different choice, then part of HS would appear in your equation of motion, not a part that diverges at the world line, but just some other part. And that actually does occur in Sam Gralla's second order equation of motion. Okay, so let me summarize what we get out of matched asymptotic expansions. So if we follow this algorithm, order by order, in R, and then from n equals 1 to n equals 2, we get that HS1, the TT component, is 4m over R, plus things that are like m times A, the acceleration, plus things that are like m times R times products of A and Riemann terms. And then so on to higher order in R. So this expansion, notice that every term explicitly features an m. Every term is directly proportional to the mass of the small object. And this expansion is known explicitly to order R to the 4. So many, many orders of R. Then I won't bother writing the form of the TI component and the IJ component, but they all kind of have structures like this. Then at second order, this self-field HS2 Now you have things that are proportional to m squared appearing explicitly. And remember I mentioned that you also get products of lower order s terms with lower order r terms. And that comes in right here, where we have something like m times hr1 over r. And then it's actually in the mixed time space component where you get the spin appearing. 2 epsilon aij n I s j over r squared. And then again you have things that are like mass times first order regular field. So this second order expansion is known to order r squared. No, order r. Inclusive. So 4 orders total, 1 over r squared, 1 over r to the 0, and r. Okay, so this is the local form of the metric. Let me add known explicitly. But this is just the s part, not the r part. The r part Rn is known in terms of those special modes up to these same orders. But the values of those modes are only determined by global boundary conditions. So the self field, if you ignore the fact that HS2 actually depends on HR1, the self field only involves multiple moments that you are locally defining from the inner expansion. But the R field is going to be determined once you say, okay, I want retarded boundary conditions in my entire system, or I want reflective boundary conditions in my entire system, or whatever. They're only determined once you've specified boundary conditions for your total metric perturbation. So they're not determined by the local analysis. So all of this just comes out of the Einstein equation, but we also get what I promised. We get evolution equations for the small mass. What we find is that it's constant in time. Or you can write that probably more accurately as at least order epsilon cubed. The spin of the small object is also constant in time. Or again, really it's up to order epsilon cubed terms. So this is dd tau, or ddt in the local coordinate system. But that's completely equivalent to the covariant derivative of a 4 vector, where S alpha has components 0, Si. So what this means is that the spin is parallel propagated along the world line at this order. Then finally, we get an equation of motion for the center of mass. So the center of mass world line of the small object satisfies d squared z alpha d tau squared equal to minus a half g alpha beta plus u alpha u beta times 2h r no, missing an intermediate term times g beta gamma minus h r beta gamma times two h r gamma mu semicolon, so covariant derivative mu minus h r mu nu gamma u mu u nu. So everything on the right-hand side only involves HR. It doesn't involve anything from HS. There's no explicit appearance of the mass. There's just HR. And again, this comes from solving the Einstein equations outside of the small object. Okay. What you'll see here, not only is there no dependence on M, there's also no dependence on S. And that's because this equation, at second order, so this is the second order equation of motion. For this equation, when I derived it, I specialized to a non-spinning spherical small object. So for a spinning object, from the same analysis, if you just include spin, the results are only known at first order. And there we have d squared z alpha, d tau squared is minus a half g alpha beta plus u alpha u beta times 2hr1 beta mu nu minus hr1 mu nu beta u alpha u beta. So this is just the linear term that you see here. So dropping this piece, and with HR now being just the first order HR. And I guess to be consistent, I should have an epsilon there. And then the spin term is 1 over 2m r alpha beta mu nu u beta s mu nu. This is the spin, but now it's got two indices. What this is in the local coordinates is delta mu a delta mu b times epsilon a b c s c. So it's just the Levi-Civita symbol that takes you from one index to two indices. Ah, yes, thank you. Thank you very much. Yes. U, that's U, mu, U, nu. Yes, thank you. Okay, so the second order equation over there doesn't have a name, but this equation, different pieces do have names. This piece is called the Misa-Ta qua force. And this is what's usually considered to be the first order self-force. It was derived by Mino, Sasaki, Tanaka in 1996, and using a totally independent, different method by Quinn and Wald a few months later. This term here, I guess I should make clear that there's an overall order epsilon squared missing, so this is lower order than that. This term here was first derived by Matheson in the 1930s, and like 20 years later, re-derived by Papapetru. But for some reason, for many decades, it was called the Papapetru force, not the Matheson force, even though he got it 20 years earlier. But now I think most people call it Matheson-Papapetru. So the way they derived it was not at all the way the things are derived here, but using just the matched asymptotic expansions, you do get this term in your force. So actually one of the kind of foundational things that still needs to be done is to extend the second order equation to include spin and quadrupole moments. Although we have a very solid idea what the result is going to be from other analyses, such as the test body analyses of Matheson and Dixon. We have a very good idea of what we're going to get, but someone still needs to do it. Okay, now you can rewrite these in a very suggestive form. So let me call this equation here, star, and this equation 2 stars. So the star equation we can rewrite as second derivative in the effective metric, g plus hr, d tau squared in the effective metric again. So the covariant derivative is being defined in g plus hr, and the proper time is also being defined in g plus hr. Acting on same world line is just the spin term, r alpha beta mu s u beta s mu nu plus order epsilon squared corrections. So this is actually, so this is star again, this is actually the motion of a spinning test body. In the effective metric, G effective is G plus HR. So this spinning small object is moving as if it were a test body in this effective external metric. And similarly, the second order equation you can show is completely equivalent to the motion of a test mass, so not a spinning body, but just a test mass, in the effective metric. So this is just rewriting double star. It's completely equivalent to geodesic motion in the effective metric. So if you just take the proper time and the covariant derivative in G plus HR and you re-expand in powers of epsilon, you just recover exactly this equation. geodesic equation in the effective metric. So through second order, a non-spinning spherical object moves as a test body in what locally looks like the external spacetime. So this can be thought of as a generalized equivalence principle. So one thing that I actually should have emphasized here is that at 0th order, or leading order, we just get the ordinary geodesic equation in the external, just G, not G effective, just G. So matched asymptotic expansions actually gives you a proof that a sufficiently small object moves as a test body in just the background spacetime. So sometimes people will say that that's a postulate of GR, that the geodesic equation or the equivalence principle telling you that all sufficiently small things move on geodesics. People sometimes think that's a postulate. I do not think it's a postulate. You can just prove it using matched asymptotic expansions. And then this is giving us what are the corrections to that geodesic motion. And what we're finding is that the corrections take us from geodesic motion in the background to geodesic motion in this effective external metric. So this is why it can be thought of as a generalized equivalence principle. It doesn't depend on the structure of the object at all. It's just true for any small mass, as long as it's non-spinning and has no quadrupole moment. Okay. So all of this tells us that the particular HR I've defined, or the particular G effective I've defined, has fairly nice physical properties. It's a vacuum spacetime on the world line, and the world line is a geodesic in it. So it's nicely physical. But you don't want to over-interpret its physicality. It is just an effective thing. There's no unique way to think of it as the specific external spacetime. You can choose different G effectives that are still vacuum equations, and you still have geodesic motion in that spacetime. So for example, if you change my local expansion at order, r to the 10, that's not going to impact any of this. And you can easily move things around to make sure that it's still a vacuum spacetime. So you shouldn't put too much emphasis on the physical interpretation, but it is nice that you do have this pretty nice physical interpretation. So the way I've defined my effective metric, or my HR, is just by putting certain pieces of this algebraic solution, or this algorithmic solution, into HR and other pieces into HS. You can, say, take one of those special modes that go into HR and just put that into HS instead. HR is still going to be a vacuum solution. And if that doesn't appear directly in the equation of motion, the motion is still also going to be a geodesic in that metric. So you do have freedom in moving regular pieces into the singular field while still preserving the nice physical interpretation you want. Now, it might be that if you go to high enough order in perturbation theory, eventually you'll reach a point where, that piece would have come into the equation of motion through nonlinear combinations of things. So it might be that eventually you do arrive at something somewhat unique, whereas this is not unique at all. But again, the two other definitions that have been given of the singular and regular field at second order do not satisfy these conditions. So even though this is not unique, it's somewhat constrained, and you can make choices that don't satisfy these nice physical conditions. The ultimate equation of motion and the ultimate Einstein equation you're solving are identical. It doesn't depend on this choice. It's just what it looks like when you write it down. Okay. Now here we're still thinking of a small extended object, whereas before we were thinking of a point particle. So how does all this relate to the point particle approximation? can we recover the point particle or point mass approximation? The answer is yes, but only at first order. Okay, so how do we show that the point particle approximation is correct to use at first order? So we have that h bar 1 alpha beta is 4m over r delta t alpha delta t beta plus order r to the 0 corrections. So this is actually exact. This is the leading order piece. And we can ignore the corrections for this discussion. Okay, so this was all defined outside of the small object. But now let's just analytically extend it down to r equals 0. So let's think back to the space-time picture I had. Time running that way, and I have some object in there. Could be a neutron star, could be a black hole, whatever. I'm going to take the self field that I defined around here, or rather take the full field I find around there in the buffer region. So say out here is the buffer region. I'm taking my analytical expression for the field in that region, which is 4m over r, and I'm just going to analytically extend it down to all points r greater than 0. So what's happening there is I'm just putting in an infinite throat. And I'm just getting rid of the real metric in that small region. So if I do that, so extend to all r greater than 0, then we can show that this is exactly the metric perturbation that would be sourced by a point mass moving on the world line. And the world line is where this thing ultimately blows up to infinity. Okay, how do we show that? Let's define what we mean by the source. Define the first order stress energy tensor to be minus 1 over 16 pi times the linearized Einstein tensor acting on H1. So then what is this as a distribution? To find out what it is, well, first we note that H1 is integrable. Should be an H bar. H bar 1 is integrable, even though it's singular at r equals 0, it's still integrable, meaning if you take the absolute value and integrate over some small region, it's always finite. And then you use the fact that a linear operator, like this capital E, when it acts on an integrable function, is defined by how its adjoint acts on a test function. So let me explain what that means. So how does E alpha beta h bar 1 act on a test function? E alpha beta of h bar 1 integrated against a test function phi. Because this is integrable and this is a linear operator, this is actually defined to be h bar 1 alpha beta times the adjoint of E acting on phi integrated. Now, if you haven't worked much with distributions, you may not know that E is self-adjoint, so you just get E again there. And now, if we want to find the full T, we can put 1 over 16 pi outside with a minus sign. And then, with a little bit of calculation, you find that what comes out here is just the mass times phi tt at t and xi equals 0, so on the world line. So you get this by substituting this for h bar 1 and doing a few manipulations, and out pops this. But this is exactly what you'd get if you put in a delta function for the stress energy tensor. We write one more line. So this is m phi alpha beta evaluated on the world line at time t, contracted into u alpha, u beta. So u alpha, u beta just picks out the tt component, and then on the world line, I can just raise the indices with the Minkowski metric, and so tt just moves up and down like that. Okay, so this is exactly what you'd get if as t1 you put in a delta function moving on the world line gamma, u alpha, u beta. So this u alpha, u beta is the same as this u alpha, u beta, except I've got indices in different places, times this delta function that we talked about earlier, square root minus g, d tau. So once you've analytically extended h1 down to all points greater than, or all points with r greater than 0, the stress energy sourcing it is just exactly the point particle stress energy we assumed we could work with earlier on in the earlier lectures. This method does not work at second order unless you choose a very finely tuned gauge. But in general, in a gauge invariant way, you cannot do this. Okay, so but this is based on having done this analytical extension down to all points off of the world line and just picked up the body and chucked it out of the space-time and replaced it with this singularity. But why is that correct to do? It's correct to do because all we've done is changed the metric in this region here. We have not changed the metric outside. That metric is exactly the same as it was before. And remember that my regular field already looked identical to a Taylor series being expanded around the world line. And so if we're not changing that field out here, farther away, then we're also not changing the coefficients in the Taylor expansion around r equals 0. So not only are we not changing the metric further away, we're also not changing the HR that appears in the equation of motion. We still have the correct HR in that equation of motion. So we have not affected the physics that we're interested far away, or the motion of this object. We haven't affected that at all by making this analytical extension. We've just changed things in this tiny, tiny region, because remember, this whole region is order epsilon, basically. So it's extremely tiny, tinier than you'd ever have in your numerical grid anyway. So you don't care about that as long as you're getting the correct things away from there, and as long as your object is moving correctly. So this is called a puncture method, and it's very, very similar to the puncture method that's used in numerical relativity, where you have just an analytical extension from outside your object to inside. So this works even for neutron star, though. This works for any kind of object in there. It doesn't matter what the object is. We found the metric locally outside. We analytically extend that local solution down to r equals 0, and we get the correct solution far away, just like we wanted. OK, so that's the end of the discussion of matched asymptotic expansions. I have one more section I wanted to cover. So I'm going to cover that actually in the first half, maybe, of the tutorial in the afternoon. And that's going to cover what's very important, which is why I want to do it. It's going to cover how to actually use this output from matched expansions in an actual practical calculation of the global metric and the self force. So we'll cover a couple different methods that are used to do that. So hopefully everyone shows up for the tutorial this afternoon. OK, but questions about matched expansions? Yeah. The existence of the buffer zone. So you always have the existence of a buffer zone, because you're only requiring that r is much bigger than epsilon and much smaller than epsilon at 0. So you have a huge range of possible values in between there, always. But in this limit, there's nothing special happening as the small object goes through the horizon of the big object.
But you need to match these, right? So
Yeah, but it doesn't matter. Unless you're a string theorist, the space-time around the big black hole's metric is just some vacuum space-time. It doesn't matter at all. So no, it's completely unaffected by the passage through the horizon. So basically, we have a Schwarzschild horizon here. So this is sky plus. This is, well, not a Schwarzschild horizon, a big black hole's horizon. And your small object plunges in. And then the buffer region is a tiny, tiny, tiny little zone right there. Epsilon is tiny. The radius of this... The only time things are going to get screwed up is when you get here. Because there the radius of curvature is tiny. So there you don't have this separation of scales between the external length scale and the length scale of the small object. So yeah, so there's no problem following it through the horizon. As long as this big black hole is big enough but it is big. I mean, the scale in here is still capital M. Capital M is unchanging. Yeah. So yeah, I mean, you're always assuming that this is much, much bigger than this. And as long as the radius of curvature is still of that scale, you're perfectly fine. When you get arbitrarily close to this, then the things will break down. Anything else? Yeah. Yeah. I don't think so. So going from, well, new physics or new accuracy for Lisa? So for physics, I think the big jump is going from first to second order, because that's where nonlinearities appear. And then you do get all kinds of effects that I will not discuss in these lectures. But you do have a lot of new physical effects because you now have nonlinear interactions filling the entire space-time, creating new linear perturbations. And so then you do get interesting new stuff happening. Third order, I don't think anything special is going to happen. It's the exact same physics still happening. And like the kinds of things we encounter at second order are the kinds of subtleties that post-Newtonian theory encountered at 4pn, where you actually get these infinite integrals over the past history. Those appear for us at second order. In terms of accuracy, this is already going to be so slow to generate a single waveform that I think the cost-benefit is not, the cost is too high for the benefit. Anything else? All right, break for lunch. Thanks.